Section 5.3 Double angle formulas. Double angles. So the name tells you what this is about. It's when we take the trig functions and think about sine to a, cosine to a, that's what the double means. Is there a formula for this? And if so, what is it? Well, some people might think, hey, I can just take the 2 out and get this. The answer is no, we can't do it this way. And you can test it. You can pick a value for a. Let's say a equals 30 degrees angle, and then substitute it on both sides. This will not work out. So when you say sine 2a equals 2 sine a, means it's gonna work regardless what a is. It's gonna work regardless what a is. Now, if I want to do or see what is the formula for sine 2a, we can use what we learned in the previous section and rewrite in a tricky way or a magic way that 2a as a plus a, and apply the formula we learned in the previous section. Sine a cosine the second angle a plus cosine sine. So b here is like a. But notice these two things that I just wrote down, they're identical. So I can just say 2 sine a cosine a. So this is the double angle formula for sine. Double angle formula for sine. How can we apply this? Look at an example. Let cosine A be negative 3 over 8, where A is in quadrant 3. Find sine 2a. So how do you find that? Well, the formula, we just said it's 2 sine a cosine a. Sine a is what? We don't know, but we do know cosine is given negative 3 over 8. We have a triangle. A is here. Cosine adjacent over the hypotenuse. Or you can use the Pythagorean identity to solve it. I use triangles, same way. To find sine A, I need the opposite over the hypotenuse. So I know the hypotenuse is 8, but I need to find the opposite. So how do I find the opposite? We're going to use the Pythagorean theorem. Call this y or something. So y squared plus 3 squared is 8 squared. Y squared plus 9 is 64. Subtract 9 on both sides, that gives us 55. So y is the square root of 55. So here we got the square root of 55. So sine is the opposite over the hypotenuse. Do not forget that we are working in quadrant 3. In that quadrant, sine is negative. And now we try to reduce this down by 2, 1, by 2, 4. Negative times negative on the top becomes positive. 3 square root of 55 over 32. That's the value for sine 2a. Can we apply it in a different way? Maybe you can be asked to prove an identity. Prove that sine 2 alpha equals 2 over tangent alpha plus cotan alpha. To do so, it's easier to start on the right hand side. And this equals to 2 over. I'm going to convert things into tan, sine, and cosine. So by the quotient identities from 2 sections prior to this, tangent is sine over cosine. Cotangent is cosine alpha over sine alpha. Now I get a complex fraction. This 2 on the top, it means 2 over 1. I look at all the fractions and I look at the denominators, find their LCD. What's the LCD here? LCD is sine alpha times cosine alpha. So we're going to multiply the top of each fraction by sine alpha, cosine alpha. Sine alpha, cosine alpha. Sine alpha, cosine alpha. Notice what cancels out here. The top, nothing cancels out. 2 sine alpha, cosine alpha. Cosine cancels. That will leave sine square alpha. And this cancels. That leaves cosine square alpha. Wait, what's sine square plus cosine square? Remember, that's one of the most important identities in trig. That's 1. Anything over 1 is the thing itself. What is 2 sine alpha cosine alpha? Well, that's sine 2 alpha. And that's what we were looking for. That proves this identity. Let's look at another example. What about proving 2 tangent theta over 1 plus tangent square theta is equal to sine 2 theta? Which side do you think is easier to start with? Well, remember, always go from the larger side. Try to go to the smaller side because you will have more options to work with. So I'm gonna start with the left hand side. And I'm gonna go to the right hand side, get to the right hand side. How do we do so? Well, I know sine 2 theta on the right side is 2 sine cosine. So that motivates me to convert everything into sine and cosine. So that's cosine over sine over cosine. And this is sine squared theta over cosine squared theta. We multiply by the LCD because that's a complex fraction. The LCD here is cosine square. So we multiply the top of each one of them by cosine square. Cosine square. Cosine square. What does that give us? 2 sine theta. This goes away with 1 copy. That leaves 1 copy of cosine. Denominator, we have cosine squared theta plus sine squared theta. What do we have on the top? 2 sine theta cosine theta. Sine 2 theta. Denominator is 1. And that gives me what I need. So the more examples you do, the better you become. The easier this whole thing gets. Before we proceed more into new stuff, recall sine square alpha plus cosine square alpha is 1. From this one, sine square alpha is 1 minus cosine square alpha. And cosine square alpha is 1 minus sine square alpha. Keep these in mind. We use them all the time. Now, can I find a formula for cosine 2 alpha the same way as we did for the other one? Yes, it is. Yes, there is a way to find this by rewriting as cosine alpha plus alpha. And based on the formula from the previous section, this is cosine cosine minus sine sine. So that would give us cosine square alpha minus sine square alpha. So that's the formula for cosine 2 alpha. Can I get a different formula? Is there a different formula for this? Yes, what we can do with cosine square, if you like, you can replace it with 1 minus sine square using that formula. So then cosine 2 alpha is 1 minus sine square alpha, and then minus the other sine square alpha. So that tells us cosine 2 alpha is 1 minus 2 sine square alpha. Or what about if I want to get a third formula? I want to keep cosine square alpha the same in the first box formula up there. Minus, instead of sine square, I'm going to put 1 minus cosine square alpha. What is that going to give us? cosine square alpha, multiply the minus plus 2 copies of cosine square. So I get 3 formulas for cosine 2 theta. So let me rewrite them, summarize them here. Is cosine square alpha minus sine square alpha, or 1 minus 2 sine square alpha, or 2 cosine square alpha minus 1. In some situations, it's sometimes easier to use the second than the third, or third than the second, or the first than the other ones. So every situation is different here. Let's look at an example. Let sine A, angle A, be 1 over the square root of 3. Find the value of cosine 2A. Well, which formula would be the most convenient? I would say if I want to use the first one, I need sine and cosine. I only know sine. If I use the last one, I need to solve for cosine. But the middle one, the second one, that would be the most convenient one because you only need sine to find cosine 2A. So the formula is 1 minus 2 sine square alpha, A in this case. And notice how this is given to us, 1 over square root of 3 square, which is 1 minus 2 times 1/3. And that gives us 1 minus 2/3. Combine them, you will get 1/3. So do you see, depending on the situation, different situations, we approach it in a different way. Let's look at more examples. What about we are asked to prove something like sine 2x minus 4 cosine x sine cube x equals sine 2x cosine 2x. You can start from either side. When I learned this method the first time, and let's say my professor goes from the left side to the right side, I used to, if he or she proves left to right, when I go home I did try to do from right to left. That helped me to become really good with proving identities. So the same thing here, we can only start trying to go from one side. Let's say I'm going to go from the left side. What is this? Sine 2x, I know it's 2 sine x cosine x. Minus 4. Keep this the same. I don't have a formula for either one of them. One thing we can do here, I can do some factoring. Factor the 2 out. Factor a copy of sine and a copy of cosine. What is left is 1 minus, I need the 2 because 2 times 2 is 4. I took a copy of cosine out and 1 copy of sine. That would leave 2 copies of sine. But wait, notice this part here, that's sine 2x. If you look on the upper right side of the page, I need sine 2x, and that's really sine 2x. What about this, 1 minus 2 sine squared? That's really cosine 2x, and that's what we were looking for, is to prove this identity. Now, is there a formula for tangent 2a? Yes, there is, and you can prove it by rewriting as tangent a plus a. It will give us 2 tan a over 1 minus tangent square a. That's the formula for double angle for tangent. And notice we're going to be focusing only on sine, cosine, and tan, because if you know these, you can get the other ones, the reciprocal of those. How can we apply this? Let's say we are asked to simplify 2 tangent 22.5 degrees over 1 minus tangent square 22.5 degrees. Well, if I look at the one right above this, that tells me A is 22.5. So if I want to go backwards, so this thing here equals backwards is tangent 2a, so it's 2 times 22.5. So that gives us what's tangent 2 times 22.5, that's 45 degrees. And we know from before, from the table, tangent 45 degrees is just simply 1. What about if tan A is given 12 over 13? Find tan 2A. So we need to find the value of tangent 2A. Well, we know the formula. Apply the formula. Rewrite it. This way it's easier to memorize every time you do a problem on this. Now, 2 times tangent is given 12 over 13. 1 minus 12 over 13 square. And let's see what we get. We get 24 over 13. 1 minus 144 over 169. The LCD for those, because it's a complex fraction, LCD is 169. So you can multiply 13 by 13 if you like here, 169, 169. And then this gives us 13 cancels, 24 times 13, 169 minus 144. And what we need to do is we can multiply the top ones, the 24 times 13, and that gives us 312. And we can simplify by subtracting the denominator numbers 25. And that gives us, if we need to divide it out, that gives 12.48. Can we look at more examples? Determine the value of sine pi over 8, cosine pi over 8. So that looks like 2 sine cosine to me, but there's no 2, 2 is missing. So the easiest way to do this, let x be this, this given piece of information. So let x equal this. I need to find the value of x. Because I said 2 is missing, because that looks like 2 sine alpha cosine alpha. So let's multiply each side by 2. So each side by 2. Again, this looks like, as this is angle alpha here, that's angle alpha. So what do we get? 2x equals 2 sine alpha cosine alpha. The formula is sine 2 alpha, so 2 times pi over 8. Let's keep this the same. This is sine pi over 4. Sine pi over 4. Now we know what sine pi over 4 is from the table. Pi over 4 is 45 degrees, so you can rewrite this as 45 degrees. And we know what that is. It's the square root of 2 over 2. If you multiply both sides by 1/2, then x would equal to square root of 2 over 4. And that's actually, before I box it, that's what we need. That's exactly what cosine pi over 8, sine pi over 8. This is square root of 2 over 4. So notice the first thing is we focus on sine, cosine, tangent, double angle forms for these. Now for the other ones, just in case if you like to know how to find the other ones, the other trig functions are reciprocals basically. So like secant 2a, it's 1 over cosine 2a. Cosecant 2a is 1 over sine 2a. And cotan cotan 2a is 1 over tangent 2a. Reciprocal functions. So if in case you come across any of these, you can use the reciprocal identities to help you. But our main focus, as I said, it's about sine 2 alpha or 2a, cosine 2a, tan 2a, because the other ones can be automatically or easily found. That's what this section is about. What are double angle formulas, how we use them. You notice how we could find sine, let's say 2a or cosine 2a, by giving us either cosine or sine. And then also that help us to work with the decimals, like the one I showed here, like tangent 22.5 without using calculator. So we were able to find it without a calculator. For the example I showed here, this example, I can show a different example if needed. Let's say they ask us to find the value of 2 sine 15 degrees cosine 15 degrees. How do we find that out? Again, this looks like 2 sine alpha cosine alpha, which we know it's sine 2 alpha, the formula. So alpha here is 15. So what do we get? This equals sine 2 alpha, so equals sine 2 alpha, so 2 times 15. That's what alpha is. And that gives us sine 30 degrees. And sine 30 degrees is 1/2. So that's what we're looking for. One thing to note in this section and the previous several sections, almost in every section, even until the end of this textbook, we will be always referring back to the table. The values for sine, cosine, tan, cotan, secant, cosecant for the main angles, the common angles, such as 30 degrees, 45 degrees, 60 degrees. Those are the acute angles that we use them a lot. And then there are other angles such as 90, 120, 150, 100, 225, 270, 315. So that's why the table is very important, because every section we go over, we use them. At some point we must use them. Also, the identities that we have been using, the Pythagorean identities, like sine square alpha plus cosine square alpha is 1. That's important. The reciprocal identities, the ones that I just showed you, we have the quotient identities. The tangent is sine over cosine and cotan is cosine over sine. By now you should have a sheet of paper where you summarize all these formulas in it for a quick reference. Any tricks and strategies you come across, write them down. This way you make things easier to refer back to on just one piece of paper. And this is the end of this section 5.3.